In this video, we're going to go over the exam review number 4 for our AP Statistics exam. This is probability and random variables. You will find all this material in Unit 4, which is chapters 5 and 6 of your textbook. Let's get started. So we talk about, in general, probability is the chance of something happening. So we use the term probability very loosely in some cases. What's the chance of this happening? What's the probability of it happening? We don't really always know, but sometimes we can do simulations or calculate some probabilities that might estimate the theoretical probability. So you could have something called a simulator where you have heads that it's a 50% chance of getting heads, and with one flip, it's either going to be tails or heads. So you're either going to have 100% of them tails or 100% of them heads, but eventually, over the course of time, that'll even out to roughly around 50%. So we can simulate that, and that's called the law of large numbers. Law of large numbers. After many trials, the relative frequency of outcomes will approach their probability. So there's a lot of formulas and our probability rules, but a lot of it can be summed up with a couple of things to know. All right, we talk about things like unions and overlaps versus intersections. So let's talk about the general addition formula first. This is one of the formulas that are found on your formula sheet. You don't have a lot on your formula sheet, but this is one of them. And what that means is, using this formula here, the U means or. So it's like A plus probability of something event happening plus the other. But that upside down U, that's the and. That's their double counting. We want to subtract that because we don't want to count that overlap twice. So as a Venn diagram, what that means is if I added A and B together, well, that's already there. So we have to take that away, that overlap away, so that way we're not counting it twice. And the union means just everything combined together. Okay, so a Venn diagram hopefully helps you visualize what that union means. There's a couple of things called complements and mutually exclusive. So real briefly here, if things are mutually exclusive, they cannot occur at the same time. So there's no intersection, so we don't have to worry about double counting. All right, the probability of something is not occurring at the same time as the other, you just add them together. And then complements, well, complements is, hold on a second. I had to find my diagram. Complements are the knots. So if you see something like, hey, what's the complement of this happening? It's not happening, and we subtract that from 1. So you might have seen some formulas where it was like NP 1 minus P or whatever. That's the complement. Okay, complement is subtracted from 1. We can do something called conditional probability, which is focused on the word given. So when you read that, you say A given B. And formulaically, it's the intersection divided by what's given. Just intuitively, you think you want to divide, you want to take what the and is and divide by the given. So I like to just refer to this formula as and over given. So as a Venn diagram, that could look like this, where the overlap on these are the 101, so that's your numerator. And then the H is not just the 101 and the 48, but together, if they add those, you get 149. That's everything within the H, so it's 101 out of 149. That would be that probability for T given H. You can do tree diagrams, excuse me. So this diagram is a little bit hard to see, so I have a different one here. So with a tree diagram, the approach is if you follow the branches, these two here must always add to 1. So in this case here, we have two events. We have the event of getting higher than average ACT or GPA versus being admitted to your dream school. So these two would add to 1. So if you're only given this number here, you'd have to subtract it from 1 to give the below average ACT or GPA. So together that form 1. Now you have two paths. You might be admitted to school if you have a higher than average GPA, or not admitted to school if you have a higher than average GPA. Or if you have a below or average GPA, you could be admitted to school or not admitted to school. Really depends, right? So when we're looking at a problem, a lot of times we have to multiply along the branches. So 0.65 times 0.83, that's 0.54. 0.35 times 0.39, that's 0.14. And you might be asked a problem where given A, so given you have been admitted to your dream school, what's the probability that you have a higher than average ACT or GPA? And so in this situation, you want to find the overall admitted. So there's two ways to get admitted, right? There is the path 1, which is when you have a higher than average ACT, which is the 0.54. But there's also the path 2 when you have a below or average ACT, which is 0.14. Together, that's your given. And then the numerator would just be the one from the H, because the event of having a higher than average ACT GPA and the overlap with being admitted is going to be just the 0.54. And so if you divide that out, you would get that probability. So true diagrams can be used a lot of times for conditional probability. It's really helpful. With independent events, independent is when the chance of one outcome does not affect the chance of another. Don't be confused with mutually exclusive. Independent events might be like rolling a die. If you roll a die, the probability of getting a 6 is the same each time you roll. Whereas dependent events or not independent events might be pulling from a hat and not replacing. So to kind of couple not independent, you might think, let me just write this out for a second, independent. An example might be sampling without replacement. And that does change the probabilities. For independent events, there's a multiplication rule. When I want to know the probability of one event happening and the other, I'm going to times them together. I have a couple examples here I want to share. Let me clear this up. So first of all, the general rule, I like this, I stole this from the Skew the Script slides because they're really nicely organized. Two events A and B are independent if knowing the outcome of one event does not affect the probability of the other event. So with that in mind, consider this. You have a scenario where you have short and tall people, low earners and high earners, and you want to know, hey, are the probabilities of being tall and the probabilities of being tall given you're a low earner, not a high earner, this is complement, so we'll say low earner. And we want to compare those two independences to see if they're probabilities to see if they're same. So what we'll do is we'll say, all right, probability of being tall, that's 123 out of 192. And that's about 64.1%. And the probability of being tall given you're a low earner, that's 22 out of 43. Well, that's about 51%. So those two events, tall and low earner, are not independent because they're different numbers. So that's how the independence rule works with multiplication. Talking about intuitive probability rules, probabilities are always between 0 and 1. The complement rule means that you just simply want to subtract from 1, or means to add, don't double count. Given is always what you're dividing by, and is means multiply, but also and means overlap in the sense of a Venn diagram or a two-way table. And we want to adjust for dependence if that's the case. So if you're sampling from a replacement, let's say you have 10 marbles, and you pull out one marble, so that denominator is going to change. So you want to affect that in your calculations. Random variables are simply put related to probability distributions. So we talk about a random variable in this situation. Let X be the winnings from a $100 bet on black. And we have basically two outcomes in this situation, in this scenario. We have $100. You win $100 if you get on black, so 18 out of 37 are black. And in this case, you lose $100 if you get on red or that green, so it's 19 out of 37. As you can see, those are slightly different, right? Because there's an odd number, so it's not going to be like perfectly equal. But the expected value, this is a random variable. The expected value is the average of those. So when you're going to see things like the mean of a random variable, here, let me talk about that before I display that. That's the same thing as the expected value. So if you're talking about like a scenario where you're trying to calculate that expected value, what you'll do is you'll take the probability associated with that value and times them together for all of them and add them together. And overall, your expected value will be likely a decimal, sometimes a negative, sometimes a positive. If it's talking about money, the negative means you're losing. If positive means you're winning, right? That's your expected value on a play of roulette here, $100 bet. There's things like discrete random variables and continuous random variables. For most of our work, we're talking about discrete because it's countable. Where continuous, we're talking about things like time and measurements and stuff like that. And those are a little bit hard to do, but a lot of times they fall under things like density curves and normal distributions and stuff like that. So continuous might be like that, whereas discrete might look something like that when you have different probability distributions associated with them. Here's the generic formula for probability for a discrete random variable for expected value. It is the item times its probability plus the other item times its probability plus the other item times probability, et cetera, et cetera. Then for the standard deviation, it's the item minus the mean squared times the probability and the sum of all of those. Now, this one here, you're probably not going to use a whole lot. Maybe for this one, because it's pretty simple to multiply and add, multiply and add. Here's what the formula looks like on the formula sheet. So this PI, or this P1, or PI, it's just P X of I. I don't know why they put the X of I instead of the I, but that means the same thing. So it's the same formula, a little bit less detail on the formula sheet. I'm going to show you a sample distribution on my calculator and show you how simple it is to get a mean and standard deviation. Okay, if you want to take a look at my calculator, in my stat menu, I put just the numbers 1 through 7, 1, 2, 3, 4, 5, 6, 7, and various probabilities. Notice they all added to 1. And I want to show you how you can get mean and standard deviation without necessarily having to multiply and add or do all this square root stuff to get the standard deviation. What you'll do is you'll put them in L1 and L2. You go to stat, one variable stats. But in your frequency list, make sure to do second too, to put that probability list in there. And in there you can get your mean, that's your expected value. And then your standard deviation, 1.81, would be from using this formula. So you don't have to go through that whole process. All right. When we're talking about making probability distributions being shifted, I want you to recall a couple things from a previous lesson. When you're adding or subtracting, this is a linear transformation. It does not affect the spread. So in this case, adding 6, we'll keep that standard deviation at 2. The center is going to be the shifted left or right if it's being added or subtracted. The spread remains the same, the shape remains the same. When you're multiplying, that not only affects the location, so 4 times 2 is 8, but it also affects the spread. So the standard deviation would be doubled in this case to 4. So it multiplies the standard deviation by that constant. If you have the variance, which is the standard deviation squared, it multiplies that by the squared constant, and the shape remains the same. So in general, we can use the rules down here. These are linear transformations where you're adding or multiplying. So we're not talking about anything fancy, no powers or anything. But the shape is always going to be the same. The center will always have addition and multiplication, but the spread will only have multiplication. Don't worry about the absolute value. We just multiply it by whatever number it is. But if it is negative, just make it positive and multiply it by that. The spread will always be only affected by multiplication, not addition or subtraction. Okay? Now, if you're combining random variables, this can be a little bit more involved. So bear with me here. If you are combining random variables and you add them together, then their means are going to be, simply put, the sum of those means. So expected value in this case here, you just add them together. When you're subtracting them, the difference is going to be their difference. So there's no trick on those. When you're adding or subtracting random variables together, we simply add their means or subtract them depending on what's asked. Now, standard deviation is a little bit different. Standard deviation, when you're adding random variables, we don't add their standard deviations. We square their standard deviations, we add them, and we take the square root. It's kind of like the Pythagorean theorem of statistics. So this is more or less going to be kind of like Pythagorean theorem. I'm just going to write it there, even though it's not really what it is. You can think of it like that, where you're squaring those standard deviations to get your variance, adding them together, and then taking the square root at the end. And that applies not only for adding, but subtracting. The spread still increases when you subtract distributions, so you will never, ever subtract variances. You'll never, ever subtract them. You'll always add them, even if your location's being changed, the spread gets bigger. So that can be summed up here with these formulas. Always addition. Whether it's minus there, it's always plus. Couple other probabilities to consider. Binomial. Binomial probabilities are when you have a fixed number of trials. For instance, if you have you're throwing 8 basketball shots, what's the percentage that the probability that you get 3 out of 8 in the basket? So we can use something called binomial PDF or CDF in the calculator. I'll remind you where that is. But we're looking for a couple things on binomials. Binary, so it's like a success or failure. Independent trials, one can't affect the other. We have a fixed number of trials, so like that's kind of like your X value. And then the S is the probability of success. So what is that probability? If you're given that probability and you have the other 3 conditions are met, you can do what's called a binomial situation. So let's look at this problem. When Wilt Chamberlain shot granny style, he made 61.3% of his free throws. Say that Wilt shoots 8 consecutive granny style free throws. Assuming that each shot is independent, what's the probability that he makes exactly 3 of them? So we have binary, each is independent. We have a fixed number of trials. We have 3 of them. Trying to find we have the count that 3 of those successes, and we know the probability of success. So to answer that question, we can use this formula provided on the formula sheet. But if you do that, then you have to know how to get that binomial coefficient. So in best practice, we want to use what's called the binomial PDF or CDF if you're combining on the calculator. So a really quick rundown of the binomial. So you're going to go to second var's binomial PDF. And if this situation was, what's the probability? Here, I'll pull this up again because I forgot the question. What's the probability he made 3 out of 8 shots? So your trials would be 8. Probability is 0.613. So from based off his previous information, probability of getting it in the basket is 0.613. And we want to know what's the probability of 3 out of 8. PDF, because we just want to know one function. And that's about 11.2%. Now, if you're asked what's the probability he makes 3 or less shots, all right? So in that case, you're combining your efforts. You would not do a PDF. You would do a binomial CDF, which is down here below it. So if I want to know that, it's still going to be the same probability, same trials, 3 or less shots. Difference is that's not just adding, that's just not with 3, that's with 3, 2, 1, and 0. And if I wanted to go more than 3 shots, I would subtract that from 1 to get the complement. Because binomial CDFs always go to the left, whether it's normal CDF or whatnot. So always we have to subtract that from 1. Mean and standard deviation of binomials these are on your formula sheet as well. The mean of a binomial is always going to be NP. You might recognize that from the large count scenario. We want that to be at least 10. So you can see that right here. And binomials can approximate a normal distribution if these large counts conditions are met. So you'll see those again and again. We do that again for inference for proportions. The large counts are at least 10, but the mean of a binomial is always n times p. The standard deviation is always the square root of NP times 1 minus p. And you can honestly just plug, your number of successes and your probability right into those formula to get those if you needed to. There's also geometric. A geometric is in the sense of, what we're talking about here, just without getting too much into the formulas, is the probability that of something happening until you get it in the basket, for instance. So maybe Wilt Chamberlain is missing the shot, and he's not going to stop until he makes the shot. What's probability gets it on his 3rd attempt? What's probability gets it on his 4th attempt? So the way you want to think about this problem is what's probability he makes that his first make comes on his 5th shot. So you want to miss till you hit your make. So the way you do that is you do your knots, right? You're going to subtract from 1, multiply it by itself 4 times because you're missing 4 times. Then you do the ones that you make. So what's going to happen is you're going to have these probability density function PDF. You're going to do 1 minus the probability of success, and all the not times until you get the one that it works. So by calculator, you could do this. You could do this as a binomial or geometric PDF. You can do second var's geometric PDF, and that probability is 0.613. X value would be, let's see, 5th shot, so 5. And that's all you're putting in there. So the probability he makes it on his 5th shot is 0.0137. So basically, you're doing 0.387 multiplied by itself 4 times, so to the 4th power, times 0.613. So that's the same thing. And you can do a geometric CDF where you're getting everything below it too. So what's probably gets on its 5th shot, or 4th shot, or 3rd shot, or 2nd shot, or 3rd shot. You can add them all together, or you can do a CDF. Guys, that is your lesson. So thank you for watching. The skew the script PowerPoints I think are really helpful. So I'm making the PDFs on your review sheet because I think those are good to look through. Have a good rest of your time. Work on the multiple choice questions and ask me if you have any questions. Thank you.